Welcome to Module 204E on motor starters. Within this module, we're going to take a deeper look at not only how do we put together a motor starter and what components there are involved with a motor starter, but we're also going to look at different types of starters that we could choose for different types of applications and how to interpret our own meter readings to determine whether or not our starter is working properly. Within this module, we have 7 different objectives that we're going to cover, and we're going to do this in a few different videos. We'll start with objective 1, which is looking at the different parts that make up a magnetic motor starter. A magnetic motor starter comes with 2 basic components: the contactor, which consists of the coil, the core, the armature, the contacts, and the shading coil, as well as the overload device. The overload device protects the motor from overheating, and it does this by utilizing a normally closed contact that is wired in series with a controller coil. When an overload condition occurs, it opens the normally closed contact, thereby shutting down the contactor. In order to reset and allow the contactor to start again, we have to manually push the reset button on the overload device. When we look at the schematic diagram for our magnetic motor contactor, we need to be able to identify 2 different circuits. The first one is my power circuit. My power circuit comes from line 1 and line 2 into my contactor box, which then goes to the power contacts that are being controlled by the operating coil. Past the power contacts, they go down to the overload device next. The overload device, once again, is a set of heaters that will open when an overload condition will occur. After they pass through the overload device, they continue down to the motor. All these different aspects are all part of the power circuit within my motor controller. My control circuit is what I use to operate the contactor, and it can contain a number of different types of controls. We can use stop-start stations, heat sensors, timers, pressure switches, float switches, and so on and so forth. And there's 2 different types of control circuit that I can typically use. The simplest type of motor control circuit is the 2-wire control. This is also known as a low voltage release circuit. It uses a maintained contact switch, which could be a thermostat, a pressure switch, or in this case a float switch. This is an automated system, so it can start up and stop at unpredictable times. If we have a power outage, there's no need to reset this particular circuit as it is automatically resetting. This is great for things such as sump pumps or furnaces where we don't want the system to have to be manually reset anytime that we have a power outage. The second type of motor control circuit that we typically use is a 3-wire motor control circuit, which we have seen many times and we will keep seeing many times more. We would use this type of motor control circuit on machinery where we need to access it and we do not want this to restart if we do have a power failure. This is called the low voltage protection. The reason it's called the low voltage protection is it is not an auto resetting circuit. With this type of circuit, I have a holding contact that is in parallel to a normally open start button. That start button is a momentary contact start button compared to the maintain contact button that I would have in a 2-wire control. If I were to lose power on this particular circuit, since I'm using a normally open momentary contact start button and I have a normally open contact, this system would need to be manually reset before I could re-engage that motor. This is an advantage to me because I can take the time to inspect the equipment and make sure nobody's in any hazardous locations before the equipment gets restarted. Now that we know the parts that go towards making a motor starter, including the control circuits that we can use, we're going to look at exactly what type of enclosure, the type of starter, and the size of the starter that is needed for any specific application. The first thing we need to do is select the type of enclosure that our motor starter is going to go into. And to do this, we need to make sure that we are aware of all the different environmental conditions that the motor starter could be subject to. We need to know if there's any flying particles. We need to know if there is any condensation or running water, if it is inside or if it is outside, and so on and so forth. The 2 places inside the code book that we need to look to determine what type of enclosure to use is Table 65 and Rule 2-400. Once we've determined what type of enclosure to use, then we're going to look at the basic styles of the starters that we could choose. When it comes to the styles of my starters, I'm going to choose one of 2 different types. I'm either going to choose a Nema Starter or an IEC starter, and depending on what my application is, could change my decision as far as which one I really want to use. NEMA stands for National Electrical Manufacturers Association, and their starters come in a number of different sizes, anywhere from 00 to 0 and then through 1 through 9. Each size has its own rating for the maximum current and the maximum horsepower that is dependent on the application and the type of motor that we're going to use. An advantage we have with the NEMA starters is that they are more serviceable. If we need to replace the coil, for example, we can disassemble, replace the parts that need replacing, and then reassemble these types of starters again. These are also considered to be a lot more durable and robust, so for any hard manufacturing processes that we might have, we will consider a NEMA starter as a good option. Choosing a NEMA starter tends to be a little bit easier than the IEC starters simply because all we need is the voltage and the horsepower of the motor, and then we can match the size of starter to those two variables of our motor, and these are really good for general purpose use. We can refer to this chart in order to choose our NEMA starter sizing. On the first column we have all the different sizes from 00 to 0, then 1 through 9. And they coincide with maximum current rating as well as the horsepower rating of all of our motors. What we do need to do is know the difference between continuous duty and jogging duty. Continuous duty is a motor that you will start and it will run for hours without stopping or without any interruption. However, a jogging duty is motors that are going to stop and start frequently. The difference between these two when choosing my starters is the fact that a jogging duty motor is going to generate more heat because it's going to have more startup cycles that are going to have that inrush of starting current. An alternative to NEMA starters is the IEC, which stands for the International Electrotechnical Commission. And these starters are sized by 4 different categories. Categories AC1 to AC4. And each category is based on the type of usage, whether it is light duty or heavy duty. The IEC contactors are then sized according to the amperage, which will vary according to the manufacturer. We do tend to have a greater selection of starters with the IEC brands, and they can build the starter for your particular application. Physically, the IEC starters are a smaller size, but any products that are below 100 amp are considered to be disposable. An advantage that an IEC starter has is they are typically a lower cost than the NEMA starters, since they are not serviceable, and the overloads are not subject to ambient temperatures like the typical overloads we would find with the NEMA starter. Regardless of the style of starter that we choose, whether it's NEMA or IEC, we still have to choose a type of starter, and we can choose either a full voltage starter, which will apply the full voltage to the motor, and that can handle full inrush current loads, or we can use what is called a reduced voltage starter. A reduced voltage starter is going to limit the effects of the inrush current at startup by only allowing a portion of the voltage to be applied first, and then allow that voltage to build as the motor approaches full speed. When we do a side-by-side comparison of a NEMA starter to an IEC starter, one thing that you're going to notice is that the wiring diagrams and the labeling between these two starters are very much different. For instance, on a NEMA style starter, the overloads are pre-wired with the coil, so there is no wiring for us to do. It is automatically connected between line 2 through the normally closed overload contact and then straight to the coil. All we need to do is make sure we connect a wire to terminal 3 in order to energize the coil. We would also have the holding contact between terminals 2 and 3 on the NEMA style starter. When we compare that to the IEC style starter, we can see that the bottom section, being the overload device, will have a normally open and a normally closed contact. The normally open contact is typically used for things like warning lights to indicate that the overload has tripped, and then the normally closed contact would be my overload contact that I need to wire in series with my coil. My coil on my IEC is labeled A1 and A2, and my normally open auxiliary contact labeled 13 and 14 is typically what I would use for my holding contact. Make sure you are aware of the differences between these two different types of wiring diagrams, and I've included this particular diagram for your convenience inside Blackboard. A special type of starter that I can get in either NEMA or IEC design is the reversing starter. This type of starter can reverse the shaft rotation on a 3-phase motor, and is basically two contactors that are mechanically and electrically interlocked together. Once we are familiar with the structure of a magnetic starter and all its different components, the next thing we need to make sure we understand is how it all operates. And there's no better way to understand that than knowing the ohm meter readings that you require on different parts of the starter. Our first step is to familiarize ourselves with the wiring diagram that we'd have associated with our starters. And it doesn't matter if we have a NEMA, like we see on the screen, or if we have an IEC. We should still be able to identify the different parts within this diagram and understand their relationship to each other. The first section of the contactor we're going to look at and understand is our power circuit. Our power circuit is everything between line 1, line 2, and line 3, all the way down through the contactor and through the overload device and coming out T1, T2, and T3. There's two components in here we need to be aware of. First, we need to be aware of the power contacts that are being controlled by the operating coil M. When the operating coil is energized, these contacts are going to close. We can also close these manually by pushing down on the armature button found somewhere on the contactor, depending on what style of contactor that we have. The other thing we need to be aware of is the overload device. These are my overload heaters or my internal overload contacts. When the circuit is overloaded, these are the things that will open up and they will disconnect the power circuit going to the motor. These also control my overload contact beside it that will de-energize my operating coil. When I have my contactor without anything being pushed or anything being energized, and remember, when you're using an ohm meter, never use it on an energized circuit. What I'm expecting to find with this particular circuit is because my power contacts are open, however my overload devices are closed, if I were to meter out between line 1 and T1, or line 2 and T2, or line 3 and T3, I would expect to have infinite ohms. It should show that I have an open circuit because the power contacts are open. If I were to push down manually on the armature in order to close the contacts inside the contactor, I have now completed the circuit between line 1 and T1 and line 2 and T2 and line 3 and T3. My ohm meter reading now should read 0 ohms or practically 0 ohms. My overload device should be closed and my power contacts should also be closed at this point. If I'm getting an ohm meter reading that is not 0, then this can indicate a problem either with the power circuit contacts or with the overload device. My first step would be to press the reset button on my overload device to make sure that that has not been tripped. After that, I can also check the overload heaters individually to see if I have continuity going across each and every one of those. Remember that your continuity test can tell you a lot about what is happening inside the circuit. And with my power circuit, there's only two things that could possibly be open. And if it is not one, then it will be the other. Typically, on the top of the contactor itself, you will have access to the screws on both sides of the power contacts, as well as the screws on both sides of the overload device. The next part of my contactor I'm going to look at for my ohm meter readings is my control circuit. And this is going to include everything along this line, from point 3 through my operating coil, through my overload contact, and all the way up to line 2. Keep in mind, everything on the secondary side of my operating coil, through my overload contact, and all the way up to line 2 is internal wiring that's already been done on the NEMA devices. On the IEC device, these are all separate components and we would have to wire them in ourselves. When we are looking at analyzing the operating coil circuit, there's only 2 points that I can actually connect to, and that's terminal 3 and terminal L2 on the NEMA device. I'm going to be taking all my ohm meter readings across these 2 points, which means that I have 2 different things in here that I need to be concerning myself with. The first one is going to be the operating coil. The operating coil is a coil of wire, so when I'm doing an ohm meter reading, I should get some value of resistance within this unit. And that might be 100 ohms, it might be more, it might be less. If I read 0 ohms or infinite ohms, then there's definitely something wrong with that coil. Anytime I'm checking the ohm reading between 0.3 and L2 on a NEMA, I should get some value of resistance. The other thing I need to be concerned about is my overload contact here. The overload contact is being controlled by the overload heaters, and when the overload heaters inside the overload device open, it will also open this overload contact. If I have no continuity between point 3 and L2 on this particular schematic, then the overload contact might be open. If it is, then reset the overload device, see if that closes the contact. On some NEMA models, you're able to access the terminals on both sides of the overload contact, but don't guarantee yourself that you'll be able to do that. The last thing I can check on my starter is my holding contact or my sealing contacts. On a Nema starter, this is between points 2 and 3, and on an IEC starter, this is between points 13 and 14. This is a normally open contact, so without anything being pushed down or energized, I should be reading infinite ohms between these 2 points. After I manually push down the armature, these contacts should close, and my ohm meter reading should change from infinite to 0 ohms. If I get anything other than 0 ohms with the armature pushed in, I know that there's a blockage or something wrong with this holding contact. It's a good idea to go over this drawing a few times to make sure you understand at which points you should have infinite values and what kind of conditions you would have 0 values and where you should find resistance or no resistance. Make sure you understand each component in here and what kind of ohm meter readings you are expecting to find, because this will go a long way to troubleshooting any contactors in the future. There will be test questions on this. You have now reached the end of 204E Part 1. Review the first 3 objectives within this module and then continue on to 204E Part 2.